Alright, in this video we're going to build an asynchronous counter, specifically a 4-bit Modulus 10 counter that aligns with the asynchronous component of the 60-second timer build. Parts list here involves most of the general pieces that we have in the multi-sim screenshot, which we'll look at in a second, with the major exception that this part here with the AND gates, this is a modification of the actual circuit logic that we need to enable the reset, which in turn provides the Modulus 10 or counting from 0 to 9 as a range behavior, specifically because we do not have a 4-input NAND gate. So this is the design, inspiring what we're about to build. Again, in multi-sim, if we built this, it would look approximately like this. We have most of the pieces we need here. Specifically, we have a 4-bit counter provided for us, medium scale integration, which just means we're being provided the working component instead of building this out with flip-flops, right? So essentially we have 4 flip-flops wired together as we would in a synchronous counter, all right? And we have access to each of those individual bits. So we're going to do 3 main parts of this build. We are going to wire up the counter and make sure that we can use the clock signal to make it count. We're going to do the same thing where we have basically a binary value indicator, which is an array of our LEDs or probes, specifically showing the individual signal outlines here. And the second part, we're going to make sure those values are correct by adding a 7-segment display driver. Adding a 7-segment display, which will be 2 components, both the display itself and a driver to turn this 4-bit signal into the actual 7-segment display signals. And then the third major logic piece, third piece overall, but the logic implementation part, or the extension to why this is not just a regular 4-bit counter, is we want a way to, again, the intended behavior of the circuit, we want a way to show a count that looks like a decimal ones place. All right, so we want to see a range from 0 to 9 in sequence. And to do that, we know that we actually need a binary value that holds at least up to 9. So we can't do this 3 bits, right? And using a 4-bit counter, we could actually go right through a whole hexadecimal unit, right, from 0 to F, or the equivalent of 0 to 15 in decimal. And so what we're doing is we are specifically enabling logic here so that instead of continuing on a normal synchronous count, that when it would otherwise go to a number that we don't want to display here, it's actually going to toggle the reset for the entire 4-bit counter, all right, which is the equivalent of toggling the reset for each of what the basically the 4 provided or encoded here flip-flops would be. All these signals will be reset when we toggle that value. And so again, the intended behavior here of our overall circuit is it appears to count from 0 to 9 as we would in decimal for just the ones place, right, for any decimal number, but in this case specifically to create the counting behavior of up to 60 seconds. So yeah, and again, that's a 4-bit Modulus 10 counter. Modulus or modulo, right, is the operator that returns only the remainder when you divide by a value. Right, so Modulus 10 is the idea that we can, even though we have more than only 10 values we could display on a segment display, right? Specifically, we know we can do 0 through F for hexadecimal. We only want to see the range of values that we would see if we were to divide a value by 10. And that behavior specifically giving us the counting behavior from 0 to 9, because the only possible remainders dividing by 10 are going to be 0 to 9. So we're seeing that same range. That's really where we get our counting behavior here. So I'm logged into Circuits Cloud here. Please make sure you log in and save your work. The only deliverable here is a screenshot of the design built and working. So you should notice when you first log in is we see these components from the first part of the course, and so the first thing we need to do here is we need to select the digital tab here for the actual digital gates and logic that we need here. And what we want to do is we want to do as we would in multisim. We want to programmatically or procedurally work through this design and try and approximate our design document as much as possible to make this easy on ourselves. And so the main component here we're dealing with is this 4-bit counter, right? And we don't have an actual 74LS93, but we do have a 4-bit counter which implements the same logic with a little less options. Again, I'm going to try and get most of these components laid out so I can start visualizing how I want to build this. And so the first thing I really need
FM 89.7 WTMD, Sounds of Reggae Rhythms. Clint Thomas here with you. And that is music coming from the forthcoming LP. It's going to be a tribute to Gil Scott-Heron and Brian Jackson. Expected to be released on May the 27th of this year. Just a testament in terms of the great reggae music coming out of the Baltimore, Washington, D.C. area. The Archives Band featuring Addis Pablo and Puma Patah, Rivers of My Fathers. And it's coming from a cover tune of Gil Scott-Heron, originally recorded on his Winter of America LP. Going to be looking forward to this great LP entitled Carry Me Home, tribute to Gil Scott-Heron. And
first thing I want to do is wire this up, make sure I can at least see it count.
Coming from the Rebellion Rises 2018 LP entitled Circle of Peace. And we heard Etana giving us a tune entitled Spread Love. Chesapeake and the Nigerians starting off the musical set with Timeless LP. No solutions in their lives for all the seekers of truth. And about right now, my friends, it is time to seal it up for this edition of Reggae Rhythms. As you move throughout, make sure...
Save early, save often.
Be healthy. Until next time, one love, one peace, one unity.
From Towson University, this is 89.7 WTMD, Towson, Baltimore. WTMD on HD1, the Baltimore channel on HD2, and online at WTMD.org.
We got our basic counting behavior. Alright, got our LEDs that look oriented properly. Remember, we are specifically building this so that we have our least significant bit here. Alright, and our most significant bit here, as we would normally read a binary value. Alright, so this should be our 2 to the 0th power, should be our 2 to the 1st, 2 to the squared, 2 squared, 2 to the 2nd, and 2 cubed, or 2 to the 3rd. Right, and this is important for our actual control logic because we want to remember what we're really doing here is we're using this counter to count for us automatically, but we want to reset at a very specific value to simulate that we're only counting from 0 to 9. Alright, again, that modulus 10 behavior. And so we've got the basic design here. Again, how you build this control structure is, I want to say, up to you, right? But please do it in a readable way that makes sense. Alright, I think the implementation here is about as easy as it can be. But again, what we're doing here from our design is we've got the clock signal wired up to our 4-bit counter. Alright, now it's got a digital clock wired up to our 4-bit counter. And then we've also got this, these probes or LEDs wired in so we can see our count in binary. And we've also added both the 7-segment display driver as well as the display here, right, which is the equivalent of this component. And so we have all this working properly. We are not yet resetting or even taking advantage of the reset functionality here on this counter. And so the last bit here is to, again, rebuild this control structure logic here. What we want to notice is what we're really doing, the intended behavior, is we're enabling this reset at a very specific point. We want this counter to show 9 for a full clock cycle, right? But we don't want to show the next value, whether that's A or 10. We want to specifically reset after 9 and before 10. So the way we do that is as soon as our outputs read what would otherwise be displayed as A, right? We're going to take those signals and provide the logic so that only in that one combination is the reset toggle. And the reason it's done with the NAND gate in the original design is it's a very convenient way to get a very specific combination of values. Notice they're having to double negate it here to flip it back into the actual toggle it, but this is pulling a very specific combination from these wires. In this case, again, where it would otherwise be reading A, right, in hexadecimal, or the binary value 1010. All right, and so this is what we're going to implement last. So again, our design, when the display reads 10, we want that to enable the reset, right? Because our value would otherwise be showing 10. So anytime we're in a count, and we would be going from the decimal value 9 to 10, or, right, 1001 to 101010, right, that's when we want to reset. So instead of using NAND, I'm going to use AND gates because this will be a relatively easy way to pull a very specific combination off these wires, because we don't want it resetting it for anything other than, right, our ceiling value. So what I want is 1010, so I'm going to take the 2 to the 0 and the 2 squared place, right, and I'm going to pull these off. I'm going to negate them, and that'll be our first AND gate. I'm going to pull the other 2 signals, which would both be on or 1 or high, right? When we would otherwise see A here, I'm going to AND those together, and then because AND is associative, all right, unlike NAND, which is not associative, which is actually the entire problem here, because we have, you'll notice over our circuits cloud, we have 2 and 3 input NAND gates. We do not have a 4 input NAND gate. However, because NAND, or not AND, is specifically not associative, we can't just use a 3 input and a 2 input NAND gate, in series. We can't just wire them together. That's not going to give us the same output. So again, the easiest translation of this logic, or one of the easier, I should say, is to simply do the similar thing they're doing here, where they're taking the inverse that signals on the, what would be the 4 in the 1's place. There you go. Alright, so there's our intended behavior. Notice you can briefly see A, but it resets before a full clock cycle on that. So again, that was the asynchronous 4-bit modulus 10 counter. And again, all you really need here a deliverable is the circuit built and working properly. Yeah, take your time, have a little fun. Please reach out with any questions, email, obviously, and good luck.